Hey, hello everyone. Welcome back to the pipelined insert sort algorithm that I made a horrible mess of last time. And hopefully this time we're going to clean things up a bit. I took care of some of the silly compiler errors from last time. We still have a million warnings. But there is one important error that I wanted to talk about, which is this one here. We're trying to compare some values in, well, just a reminder from last time, we were implementing the actual insert sort. So the code we're working on here is just simple sequential code that implements an insert sort algorithm. And this error here, where we're trying to compare two values in the list here. But the error here, there is no applicable operator greater than for private type element defined at maybe type, etc. So the problem here is we're taking in this generic package into our list, but we don't have a way to compare two elements of this package. And so we need to enforce that there is a comparison operator on these elements we have. And that's pretty simple to do, I hope. I believe that'll do it for us. So we're just adding in a less than function as a generic parameter. Well, I've got the syntax for it wrong.
Why do you
Time
put
to
it in
Google.
quotes?
Those are the parameters. Oh wait, maybe it's a single quote. I know that you need because it'll interpret less than as a function itself.
Mm-hmm.
So you need to actually you need to put in infix operators in quotes. Let's look it up. I should have double checked this beforehand. Well, let me stop sharing my screen for a moment so that I can consult some notes. Bear with me for a second.
You're right about the double quotes. And you have to use that on the function, both the name of the function, or sorry, the operator of the function that you're overloading, and the end.
Mm-hmm. Oh, that's it. I forgot to specify the return type of the function is what was going wrong. Cool. And we're back. So we need to say it returns a Boolean. And that's it, I think. Cool. Now we still have the error, and it's because we're using a greater than operator here. So we just need to swap that around to use a less than operator. And that should be that. Still 1 million warnings, and 1 million warnings in here now. Let's just fix all these up. This one could be declared as constant. Yep, that's cool. Make that a constant. Removing some various spaces that Ada's not happy with. That can be a constant. That one could be a constant, but we'll be changing it later. Shangyu asks, we don't need to implement the less than needed. No, we don't, because here it's operating on a generic type. So this type element could be anything. And because we don't know what the type is, we can't implement less than inside this generic package. At the top level, we're going to be passing in like a integer or something that'll have a less than operator predefined on it. So we don't need to take care of that.
So if we wanted to use this with a type that's not one of the standard Ada types and doesn't actually have a less than operator defined in it, we'd need to first define that operator before being able to use it with our package.
Yes.
Yeah.
Okay. Style warning's gone yet. 2 more left. There we go. Okay. There's all of our style warnings out of the way. We've just got this one unmodified variable here. Cool. So, last time we ran into all of these problems with me not being able to implement this function correctly because of Ada's subtypes and things. And I've since figured out a correct way of doing things. First of all, beforehand we had this list, our buffer containing maybe values, whereas we don't really need that. We can just have our buffer contain elements themselves. And the same for the max value. And I believe for the insert operator as well. So the only place that we actually need the maybe type here is for the overflow value that gets returned out of the insert method if the buffer is full. So, yep, we can have a list contain maybe elements, and in that case, we don't need to initialize it. And we had our buffer index up here, and we're also going to have a different size type down here. So the buffer index, it has it's the index of the buffer that we're using. And we're also going to have the buffer size type down here, which will give us the size of the buffer. The difference here being that the buffer might be empty, so we need to have the possibility of 0 elements in the buffer size type. And now I believe that's enough for us to...
Callum, you said earlier that the list contains maybe elements, but right now it looks like now the list actually just contains elements. Was that intentional?
So
okay.
Yeah, beforehand it contained maybe elements, but there wasn't actually a reason for that.
Okay, so that was a delusion.
I was just doing that for no reason. So back to our insertion method. So what do we have? It is going to take in an element that we want to insert. And down here, the first thing that we do is do a binary search to find the place where we want to insert that element into the list. And the way that we do that is we go from the, we basically look at all of the elements that we have stored in there. And because the array has a fixed size, but it might not be full, we need to constrain the space that we're searching within. So if, for example, our array is 100 things long, but we only have 5 things in there, we only want to search the first 5 spaces. So when we are finding our place, we want to search from the beginning of our list up to, what did I call that variable again? Oh, I didn't make a variable for it. We call it current size, and it'll start at 0. And we want to search from the beginning up to current size plus 1. And that'll give us the place where we want to insert our element. And we don't want that overflow in there just yet. Cool. So now that we've found the place where we want to insert the element, we first have to make space for it. So we take everything in the array from that place upwards and we shift it to the right. So I did all this nonsense with successor functions here. We can just use place plus 1. I believe that's what we want to do. So if, for example, there are 4 things in our list and we want to insert it at index number 2, then we take things 2, 3, and 4, and we move them into places 3, 4, and 5, just like that. And then we insert our element into the list, just like that. And we need to do a bit of bookkeeping and increase the current size. Now, this is all well and good until the array is full. So in the case that the array is full, we're going to run into an error where we try to shift everything to the right, but we end up going out of the bounds of the array. So we need to account for that case where the array is full. And so if the array is full, that is if the current size is equal to max size, then, well, what we do here is going to depend. Because in this case, we have a full list and we're trying to insert something. So either something's going to pop out the end of the list when we insert our new element, or the new element isn't going to go in the list at all, and it's just going to go straight out the end. So let's have those 2 cases. And that'll be... So if the element we're inserting is greater than our current max value, what is our current max value? Well, because our list is sorted, it's just going to be the rightmost value in the array. And that'll be, what did I call it? List. Current size. Yep, I think that's the correct one. That'll give us the maximum element of the array. Okay, if it's bigger than everything in the array, then we don't have any inserting to do. And we can just return the new element as overflow, effectively. So we can return just E and not do any insertion. Otherwise, we need to kick out the top element of the list. And we'll need to keep track of it so that we can return it later. So let's make a maybe element up there. And if we wind up with something getting kicked out of the list, we'll set that to be the overflow value. And then now that we've effectively kicked it out, we can just reduce the current size by 1. And then when we move into our algorithm, when we move into our part down here, when we try to do this array shift, now this current size plus 1 won't be out of bounds because we've reduced it by 1. So does anyone see any bugs with what I've done here? I think that this should be more on the right track now. Although there are now 9 errors. Oop, I haven't defined a greater than operator. I need to use the less than operator that I defined. Oh yeah, this is a type mismatch error. It's expecting a maybe type, so I just need to do just there. This error down here. Oh yeah, this is from when I removed the maybe values from the list itself. 5 more. Same error. Same error. Same error. Okay, now we're down to warnings.
It really did simplify the code a lot to get rid of the maybe type.
Yeah.
I didn't expect that.
Right, okay, and we're missing a return statement at the end of the function. Okay, so after we insert our thing into the list, what do we need to return? Well, if something was kicked out of the list to make room, we want to return that. Otherwise, we want to return nothing, which is effectively what we're tracking with our overflow variable up here. So at the end, we can just return overflow. Error's gone. One more. Style. Wonderful. Cool. And that's that, I believe. Again, let me know if you see any problems with this implementation, or let me know if you have any questions about what we've done so far. But I believe this will be a working insert sort now. Oh. Need to change our max value function. Oh wait. We didn't want max value, we want last value. Bear with me. Okay, so what I've done here, remember that we wanted to have this interface between the inserter task and the feeder task in each node. And that interface would be effectively, it would expose the last element of the list so that the feeder task would be able to tell, do I need to pass do I need to pass this element down to my inserter, or do I need to pass it on to the next feeder? And that's what this function here is implementing. So it's checking if the list is full, and if it is, it's returning the last element of the list. Otherwise, it's returning nothing to say the list isn't full yet. And I think that's about it there. Cool. Oh, another 4 errors. More type errors resulting from my changing it to use a maybe type. Cool. Now we're good to go. So we've implemented our insert sort algorithm. Now let's put that into our code up here. We've got this inserter task, and it's going to need to have one of these data types. So let's instantiate the generic package. I believe I'm using it up here. Bounded ordered list. For some reason it's expecting 2 maybe element packages, but I'm just going to ignore that. And I believe that the less than function will also be automatically put in if there is a natural one defined.
The compiler is smart enough to just discover that the less than operation is defined and pass it in as the appropriate parameter.
Yep.
That's pretty cool.
Yeah. So we need to pass in the max size and the maybe element we're using. I believe we instantiated the maybe element up here. Yep. So we can just pass in maybe element for that. And for the max size, how big do we want these local arrays to be? Well, first off, let's decide how many nodes we want. Let's just say 8. And then we can calculate based on the data stream length and the number of nodes. Just like that. So with 8 nodes and 10,000 data stream elements in total, this will give 1,250 elements to each node. And there we go. Oh, I believe we can just call it query. And how do we use this? Well, we have our insert method. So in this body here, remember that the inserter task is effectively sitting here waiting on this queue, waiting for the feeder task to send it data. And when it gets a value, it needs to insert that value into the list. And so remember that we're being passed in a maybe value, I believe, and we need to only actually insert it if it is valid. So if it's valid, we have to insert it into our list. And remember, this is going to return an overflow value. So let's capture that. Just like that. So the insert method will return an overflow value. And then so what do we want to do with the overflow value? Well, initially, while the list is filling up, the overflow values are going to be invalid. And that just means the list isn't full yet. So if the overflow value is invalid, then we don't need to do anything. But if it is valid, that means that we've kicked something out of our list and we need to pass it on to the next feeder. So if it is valid, then we need to pass to next node. And also we need to update the last value in our list so that the feeder task will have a new idea of what our max value is. So how are we tracking that again? We had a protected object max element, and so we just do we just write the last value up to there. Oh. Need a statement in there to make the compiler happy. And type errors. Oh, the protected object takes an element. We want it to take a maybe element.
Do we ever need to write the max element? Except for when we're initializing it, do we ever need to write it to anything other than a real element value?
I don't think we ever need to write it to anything other than a real element value, but initially the feeder will be comparing to it to basically, if the list isn't full yet, then the feeder wants to pass everything down to the inserter. And here the invalid value is effectively serving as saying the list isn't full yet.
Mm-hmm. So we need the possibility of the max value being invalid.
Yeah.
I think in relation to how do we pass on to the next feeder, Xiangyu says, now we need to give each task an ID and declare an entry family.
Give each task an ID and declare an entry family?
Yeah, I guess this is referring to the node tasks themselves, the feeder tasks.
Yeah. Well, we've already declared the entries, and we don't need a family, because every feeder task is just going to have a single feed entry where data comes in. But yeah, pass to next node. Well, we're going to have to call feed on the next node, but we don't yet have a next node. We haven't created the next node yet, really. We haven't tracked that anywhere. So let's do that. So there's a clever way we can do this. We can have a local variable called next node. And it's a pointer to a node. And initially it'll be a null pointer. And then once our list is full, and if we then receive more data, we can create a new node to handle the extra data that overflows from us. And there's a nice way we can implement this with a function. So we can have this function here that if the next node is null, then we can create a new node by doing next node equals new node. But otherwise, this function can just return next node. So now, whenever we want to pass something onto the next node, rather than first having to check whether the node exists, we can just use this access next function that will automatically create a new node for us if we if there isn't already one that exists. I believe we oh, we can even get rid of the else. I believe that works fine. Cool. And now down here, past the next node, all we have to do is call access next dot feed. Oh wait, dot all because it's a pointer. Dot feed. We need a type for this. So we declare a pointer type, and then we're going to use that down here. Task type cannot be used as a type mark within its own spec or body. So it's not letting us make a new node. Any ideas here, Josh?
No. Except that I'm not 100% sure I understand that compile error. Is it? Does it think you're trying to create a new type as opposed to a new instance of a type?
Maybe. I'll try moving it into the body of the node itself, rather than into the body of the subtask. Yeah, this error might need some Googling.
I also am Googling away. My Ada skills not being what they should.
Yeah.
I hope students are also Googling.
Oh man, you got my face in the corner. That's fun.
Oh yeah, there you are. You weren't there before. Not sure how that happened. Yuan says you should declare it in the declare area, I think.
It is in the declaration area here.
Right. Yeah, the begin statement is further down.
So what's going on here is we're trying to, within a node task, we're trying to create a new node. And the Ada compiler appears to not be happy with us doing that. Shangyu, it sounds like it does mean that we can't reference itself in its body. But I know that this is possible. So I'm not entirely sure what's going wrong here. Bear with me. I'm going to stop sharing my screen and consult some notes real quick. Oh, it looks like it's going to be a pretty trivial fix. I think we're just supposed to, we need to declare a function out here called new node. And it's happy.
All right, that's wild. I don't understand that.
Yeah. So the way that we fixed that was, rather than making the new node inside the task, well, rather than putting that code inside the task body, we make a function outside of the body, which makes a new node, and we call that function inside the task body. I've got no idea why Ada requires us to do this, rather than letting us type new node inside the task body. But hey, this is the language that we choose to live with.
This reminds me of sort of C forward declarations. It's okay.
Yeah, but the type
just
itself
assume
was
that the type's been
declared.
defined. Yeah, okay.
This is a peculiarity of Ada, I suppose.
Probably made some compiler writer's job easier back in the 1980s. And
yeah,
it's stuck.
Yeah. But now we have a working access next function that will give us the next node or create a new node if there currently isn't a next node. And so down here, when we overflow the list, we just pass the overflowed value onto the next task. And there's a warning up here. Hides overflow at line 70. Oh yeah, I used the word overflow for something else as well. But I think that's fine for now. We can change the name later. Now, I think we've implemented everything here. We insert it into the list. We update our max value. We check if the list overflows and pass the overflowed value onto the next node. So this now looks like a pretty complete inserter task, with the exception that we still need to program the behavior for an invalid value being passed in, which, as we'll recall, having an invalid value passed into a task is effectively the signal to terminate. So down here we'll have to program the shutdown code, but we'll get to that. I don't believe we need that there. Cool. So our inserter task looks to be done. Now let's finish up our feeder tasks. So as it stands, we've got the middle loop. They are accepting incoming data. And they are using some dummy function I've put in up here to determine whether or not to pass the value on to the next node. And if we do pass it on to the next node, well, we need to just pass it on. We can implement that now. Remember, we just pass to access next. Just like that. And if we decide not to pass the value on, we put it into our internal queue. So that body looks pretty complete, with the exception of termination. We just need to implement this pass on function up here. And so the question is, given a value, when do we pass it on to the next node, and when do we take it into our current node? And the answer to this was pretty clear from the specification. All that we have to do is, if the value, well, if our list isn't yet full, then we don't pass the value on. And the way that we were signaling if the list was full was the invalid value as the maximum. So let's check the max element and see if it's valid or not. If it's not valid, we return false, because we want to keep it. But if the max element is valid, if our list is full, then we want to pass on the value if the current value in our, well, if the value that we're looking at is bigger than everything in our array. So and also, if the thing that's being passed in, the thing that we're examining, is invalid itself, then we don't want to pass it on. And down here, if it's bigger than everything in our array, then we do want to pass it on. Otherwise, we just want to return false down there. We can make this a little bit nicer. And we can maybe fold this up a little bit more. Okay. I think that'll do it there.
Got a couple of questions about the access next and the node pointers. So Kira asks,
Yep.
What's the actual use of the node pointer? And I guess to interpret why do we need a pointer and not just a variable of the node type itself?
Okay, so up here, when we make next node a pointer, if we made this just a static reference to another node, tasks get instantiated when they are declared. So if we just had next node as a node, then when we start up a node, this node inside it would also be initialized immediately. And then when that node starts up, the node inside that will be started up immediately. And so the moment that you try to, initialize a node, you would get this sort of infinite recursion of initializing nodes over and over. And the Ada compiler actually won't let you do that. And that's why we need the pointer here. We need to, because the pointer, we can set it to be null initially. And then when we want a next node, we can assign it to be a new node rather than being null. And this gets around the infinite, that sort of infinite loop behavior. Kind of like how in any language, a type cannot contain itself, or cannot contain an element of the same type, because then something of that type would not be able to fit in memory. So, but types are always allowed to contain references to something of the same type, which is exactly what we're seeing here.
And Xiangyu's question, I think maybe it was just a misreading of the code. Xiangyu's asking, every time we call access next, don't we create a new node? Shouldn't it be a singleton? I think actually that, Xiangyu, that is exactly what Callum has implemented, unless I don't think there's any bugs there. So the first time access next is called, it's going to create a new node, but every other time it's going to return the node that's pointed to by our next node pointer.
Yeah. So we're only actually creating the next node once here. And if it already exists, then we're just returning the one that already exists. Daniel, can we just return a Boolean expression in parse_on rather than using if-else? Yes, we could. We could just roll this into a single expression and make a Boolean expression out of it. But I haven't done that. But that would be just as valid, and maybe even nicer. Yeah, moving on. I believe now things are looking pretty good. The one thing we're missing is checking for termination. But we can cross that bridge when we get to it. So our implementation is looking pretty complete right now. So we're probably ready to make some testing code. So let's make a list and try to sort it. I believe Ada has a random package that we can use. Ada numerics discrete random. It is a generic package. Cool. So we're instantiating a generic package here that'll give us random elements, which is great. And then what does that give us? Gives us a generated type. Cool. And I believe we can just do that, and that'll give us a random number generator.
Cool. So if I give discrete random any discrete type as a parameter, it's going to generate some random value of that type.
Yeah, pretty much.
That's really nice.
Yeah, so you could change this type element to be whatever you want. You could probably put in a mod type or something, and this will give you random elements in that.
Xiangyu does not like it. Why? It's not friendly. Why is that?
It's great. What do you mean?
It seems better than, like, if I do this in C or C++, usually I have to generate a random float and then multiply it by some number to put it within a particular range, or I have to generate a random int up to a particular value, perhaps subtract the minimum value. This seems a lot nicer.
Yeah. I believe we can call reset to, like, seed it or something. I'm not sure. I think we have to do that before using it. And then let's make a big old list that we're going to populate. It's going to be 10,000 long, so let's make a type. Just like that. And then we'll just initialize everything to invalid values. And when our program starts up, we'll do a for loop. What's the function called? Where is that numeric start? State save, reset image value. Random. Takes in a generator and returns a thing. Cool. So is equal to random. Oh. I got my others keyword. Might need an equals in there. Cool. Need a use clause for my random package. And looks good. Let's just do a quick test here. Finally going to run this code for the first time. Oh. Just to print out this list of random numbers that we're generating. And it appears to work just fine. We get a big list of random numbers. And now let's sort them. How do we do that? Well, we need to actually, we've got all these tasks that we've made to do the sorting. We need to actually initialize a task first. So let's make a first node. Just like that. And then let's feed all of that data into the node. And hopefully this won't crash. It doesn't crash, it just hangs, which is exactly what we wanted. Because we aren't terminating our tasks yet. But let's put in some print statements to see if we can figure out what's going on here, to see if our code's doing what we expect. So how about we print something every time we make a new node? We're expecting 8 nodes in total. As we set up here, number of nodes equals 8. And we're starting with 1. So if every time we create a node, we print new node created, that should print that 7 times in total. Oh god, it's printing that way more than 7 times. We've made a horrible mistake somewhere. So, time to start debugging.
Are we creating a node every single time we access the next node pointer?
Perhaps. Perhaps. This is a lot of new nodes. Certainly more than I expected. So where's our access next function? If next node is null, then we make a new node. Otherwise we return. No, I think the bug's going to be somewhere else. Give us any ideas if you think you have some idea how we might be able to figure out what's going on with this bug.
So how many elements are we generating here?
We're making 10,000 elements in total.
Okay.
Maybe it's a bug in our pass on function. Because if we just always pass on.
Oh yeah, then we'll always create a new node. Right, so for some reason we think that the buffer is full, or something should always spill out of the right hand side of the buffer. Yeah, showing you just come to this conclusion too. Maybe it's not full, but it's calling the next node.
Yeah. So then, what could be wrong here? Let's just check if anything's ever being passed to the local queue. Yep, lots of things being passed to the local queue. Oh, that's interesting. So we saw up here that all of that printing out, passing to the local queue, happened before any of the new nodes were being created. So we've got all this passing to local queue, and then eventually we had new nodes being created. But this time we're not even having that, we're just having passing to local queue being repeated over and over again with no new nodes. Let's try dramatically reducing the amount of data we're producing. Down to 100.
You also suggests maybe we should print out the current size.
Yeah, that's a good idea. Okay, so here we're just creating a bunch of new nodes.
So when we overflow, do we want to print out the current size just to confirm that we've actually got 10 elements? Is that the size of the queue at the moment? Sorry, the size of the
Down here?
buffer?
Wait, where are we talking?
So when we're about to pass on to the next node, should we print out the size of this node of this node's buffer?
Yeah. Okay. I don't think we currently have a method for that. Hopefully that works. Nope.
We probably have to define it in the definition in the body, right?
Yeah, because it's accessing private data.
Yeah.
Cool. What do they call it again? Get size. Well, we're getting a lot of 12s, which is good. It's bothering that we see so many new node createds in a row.
Right. Surely if we have, 100 elements, we have 12 elements per node, we should only have 8 or 9 nodes.
Yeah, 8 or 9 nodes. Let's try putting some delays into the feeding process to slow down these print statements. Yeah, so all these new node createds are very much coming all at once. So the first time we create, it looks like the problem's happening the first time we create a new node. Because up until then, it was all printing out nice and slowly.
Yeah, it's quite interesting that it doesn't, it's not like it's getting into an infinite loop of creating nodes, because it does stop creating new nodes eventually and go on and pass something to a local queue. But it seems to create a very large number of new nodes.
Yeah, maybe Shangyi was right.
So the feeder task is the node task is accepting a feed entry.
Yep. They sit here accepting their feed entry. Let's try to isolate exactly where. Oh. Actually, not sure about that. Oh, I found the problem. So here's what's happening. People are, looking at the max value that their local buffer has, but this max element protected object is actually global. There was one single
It's
max
not a protected
element
type, it's a protected object.
Yeah.
Okay.
So the new nodes were comparing to the max value of the original node. And considering that the original node just passed on that value, obviously they're going to immediately evaluate that to true and make a new node.
And you
So we need that
for that to be
protected
defined
object.
inside the node, which would then mean there's one protected object for each node task.
Yes.
Ah.
Okay. Bug, hopefully, squished. It compiles. Wonderful. Okay. I'll remove the delay statements to speed things up a bit. And
it looks like we're creating far fewer nodes now, which is nice.
Yep, for sure.
The delay was right down the bottom, I think.
Yeah, I'm just removing some print statements as well. There we go. 1, 2, 3, 4, 5, 6, 7, 8. And
the original node makes 9.
Yeah,
that makes
which
sense.
Is correct. If they're having 12 elements each, then
4
for
elements
100,
left over
we need
for
9
the
nodes.
Node.
Yeah. Well, we did it.
Xiang Yu's just saying that this is a pretty common mistake, defining a single protected object and then sharing it amongst tasks.
Yeah.
It's broken assignment 1 code before.
All right. Now, let's try to move quickly here. So, now we need to actually figure out a way to terminate our tasks. And we're going to do that just by, after feeding in all of the data, we're going to feed in an invalid value. And that's going to tell it to stop computations. Now, in that case, when it gets the shutdown signal, we don't want it to immediately pass that on to the next task, because we want to make sure that all of the values that we have in our local queue are processed before we tell the next task to shut down. Otherwise, we might have values that we still want to pass on to them, but they've already shut down because we've told them to shut down. So if we get fed an invalid value, the pass on function here will already tell us not to pass that value on. And then in this internal queue here, we're going to be putting the invalid value into the internal queue. And that's what's going to tell the inserter task that it's done and it can terminate. So none of this code here needs to be modified. It all works properly already. All that we need to do is tell it that it's done when it gets an invalid value. So let's just put in an if not current value dot valid, then exit. And that's what'll tell it to shut down. And I think that's all we need to do there. We might also need to pass out the values in here. Oh wait, no, the inserter task can do that. So how does the inserter task terminate? When it gets the signal to terminate, it needs to pass that signal on to the next node. So we propagate well, at this point we know that we're finished processing everything because we've got the invalid value from our queue. And we can just pass that on to the next node. And then we need to output our array. And how are we going to do that? Well, let's make an array for them to write their data to. So we've got our... We can just reuse the same array. I don't see any problems with that. There aren't going to be any race hazards. What do we call it? Data. So, oh wait, no, that's not going to work. Whoops. We're going to need an output queue. Element maybe size, key size. Let's make a new queue type for this. It'll take straight elements rather than maybe elements, and it will have the same queue size. I don't think there's going to be a problem with that. And we're just going to have the inserter task write all of its data into an output queue. What was it called again? Queue type. Wait, protected queue. Oh wait, we can't use a use clause there because that will hide the queues from the other one. So that should work. Not referenced. Wonderful. Oh, missed an implicit dereference down there. Need to put your dot hole in. Space required. Cool. Oh, also bug up here. Because we're going to be outputting our values through a queue, we want to make sure that we've written all of our data in order to the queue before we let the next task start writing to the queue. So the inserters need to write their own data to the queue before sending the signal to the next task. So it's just going to put all of its data into the queue and then pass along the value. And the main task down here is going to get that data out of the queue. So it's going to dequeue the data into our original array. And then let's print out the array so that we can see if it's sorted. Cool, and now we hope. Well, it's not working. Let's check if anything's being dequeued at all by printing stuff out as we dequeue it. Yep, we are getting a bunch of stuff dequeued, and it appears to be in order. Oh, no, it's not. That's concerning. Oh, wait a minute. It looks like it prints it all out in order twice, which is the intended behavior. And that's a problem. Because that means the last time we ran it, when it printed nothing, that was because we ran into a race condition. Cool, so that appears to be working. Cool. Let's do a little bit of a more robust method here. Let's actually check that the list is sorted. So we're going to loop through it, and we're going to check if any element is less than the previous element. Actually, let's raise an exception here. So we'll raise an exception saying the list isn't sorted if we detect that any element is less than the previous element. Just like that. And if we make it through that, we're going to print first is the one I want there. And the list is sorted, everyone. We did it.
Hey.
We wrote a pipeline insert sort algorithm, although it looks like there's a race condition somewhere in there.
So what's your evidence for the race condition? What's your worry? Like what's the particular
Earlier, when we were printing out the entire list, we started off the program, but nothing was printed. Oh, also, we'll note that the program actually hangs when it runs. It doesn't terminate. And the reason for that is not immediately obvious unless you've been thinking about this code a lot like I have. So here, when an inserter task tries to terminate, it enqueues all of its stuff into the output queue. But, well, and this means that if the output queue gets full, it'll be blocked here. And what does it put into the output queue? It puts all of its local values in. But this getValues method, what does that do? It returns the entire buffer. Now, we'll remember here that we have 9 nodes, and each of them has 12 elements. So that's a total of, what's 9 times 12? 108, I think. So we have 108 elements being enqueued in total. But we only have 100 elements being dequeued. So I believe the last task is sitting there hanging, still trying to enqueue more things. Because it's printing out more things than it needs. And I believe that the way that we fix that is we actually index the list. Oh, wait a minute. Buffer. I don't think that's... Ooh. I don't think that's possible without doing some serious boilerplate. So I'm not going to do that.
I think we might leave that as an exercise for the students.
It'll be
offline. Xiang said, I don't know if he was serious or joking, but he's definitely speaking like someone who's spent a lot of time on assignment 1. Maybe just delay several seconds in the main thread to avoid race conditions.
Oh yeah, that'll fix it.
It probably would fix it, but that would not be an elegant solution.
Yeah. So when you solve, air quotes, a race condition with a delay statement, you are effectively solving it in practice, assuming that the schedule is going to be nice. So anything that is solved with a delay statement, you're effectively encouraging the scheduler to give you a nicer interleaving with that delay statement, but you aren't actually preventing it. The race condition is still there in theory.
Yeah, I can think of very few legitimate uses of the delay statement, and certainly none relating to solving race conditions.
Yeah.
Actually, the use of the delay statement...
Euron. Oh my god, you are very correct. We've made an error.
This is Euron's comment. The last node creates a new node after queuing. Right.
It does. You are very correct with that. So I've made a boo-boo and I didn't see it. And Euron has. Props to you for that. When the last node finishes, it calls accessNext.all.feed, meaning if there isn't a next node, it's going to create one. And this is the one case where we don't want to do that. So we only want to do this if there actually is a next node.
Perhaps that's not the only bug in our code.
For some reason, fixing that up appears to stop our code from outputting. Huh. That's weird. I don't see any immediate reason why that would break things. Any ideas, Josh? Oh, wait. It worked that time. But not that time. It appears to work less often when we do this. And it appears to also create more nodes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 nodes.
We should certainly not have 10 nodes.
Yep. Look.
I think Euron's right. I think that is a bug. Maybe we didn't find the right fix.
Yeah.
We'll probably have to work on it some more. I did want to just, before we go, I just wanted to talk a bit more about the delay statements, because the use of the delay statements while debugging was really helpful, right? It just slows things down and changes the ordering, more importantly. Without those delay statements, we essentially have no control over the order in which things happen. And so we get our print line statements interleaved in really some random order, which potentially doesn't tell us much about what's actually happening inside the program. So that is a really useful strategy. don't leave the delay statements in your production code, but it is a good strategy. In fact, for those of you who kind of got a bit stuck with on the mid-semester exam, the task scopes question, that was asking about the ordering of different operations in tasks. And so it was just asking a bunch of questions about, oops, that's not what I meant to show, about in what order things happen. You're presented with some ADA code and then let's see, here's the ADA code. Sorry, Callum, I'm hiding you. So we've got some ADA code like this, and we're asked various things about the ordering of, say, that start of static outer task will always appear before task scopes. That was one of the statements, and we can actually easily test this just by running the code. But to do the test, we have to add some delay statements, and so this is the way that I would deal with that kind of a problem. If you add a delay statement of long enough, that essentially, if you run the code, then this you will find, in fact, that task scopes appears before start of static outer task, and therefore you'll find that you've disproved that statement. So if you can think about where to add the right delay statements to force a particular operation to take longer, you can make some more guarantees about the ordering there. Yeah, I think this is quite a nice way of debugging your code. So it was good to see Callum doing that. I'm glad we had the bug.
Yeah. So one closing remark from me. I think we probably aren't going to come back to this and fix it up. We've discovered that there are bugs in this code. So if you're looking for a fun exercise to work on to improve your concurrent skills, you can clone the lab code repo, have a look through my code, and try to fix the race condition. If you do figure out what it is, please let me know, because I'm not going to put my time into this. But I'm interested to know.
Yeah, let us know on Piazza.
Thank you all for thank you all for tolerating my floundering today. But I hope it was useful.
And no, Harry, it's not going to be on the final exam to correctly implement pipeline insert sort. But the techniques here will be useful for sure.
Yeah.
Thanks, Callum. And thanks everyone
worries.
for all your assistance. There'll be no more, chatting from me today. So I'll see you next Tuesday. We're going to start talking a little bit more about the chapel language, which will be exciting, and we'll have some topics on non-determinism next week. So see you then.
Wow, sounds like fun topics.
Yeah, I love chapel. It's a great language. All right, bye everyone.
Bye everyone.